Okay, students, speaking to my Friday students especially, we are going to go through our unit in Part 1, Electrical. So make sure that you take some notes. You're going to need those because next week, today is the 8th, so next week, which will be about the 12th and 13th, you'll be seeing a written quiz in class, and I'll be emailing those quizzes out to the students that cannot attend those. And just a side note, again, students, you do not have to bring your cars into this class. I'm speaking to my Park City students exclusively. You don't have to bring your cars into class to pass this test or this program. You don't have to bring them in, but when you do, I award anywhere from 10 to 15 extra points in an extra separate slot, so you get those extra points for going to all the trouble and bringing your car in. Again, you do not need to bring your cars in to get a passing grade in this class. With those announcements done, let's begin. We're going to start with electrical theory. Now, please don't get bored. This is not a boring subject, but it can get boring if you're not focused on the subject. So I want to talk to you a minute. Again, this is where you turn the heat down, just so you guys know. Okay. How does electricity work? What happens? What makes electricity in the world today? How did it get made? Well, I'm going to give you a magnified picture of a wire. Here is an electrical copper wire, magnified 1,000 million times, whatever it is. Inside that wire, you have subatomic particles. You have a neutron. It's made up of many subatomic particles. We'll just call this the nucleus of the atom. And then you have the electrons that go on the outside of the atom. Okay, and they go like this. Okay, now if this was a piece of wood, we would see these negatively charged electrons moving in a stable orbit because these electrons keep everything stable. Everything is bonded together. This electron bonds this electron to the nucleus. This electron here bonds this electron to the nucleus. They're bonded together. They're caught. They're in a bonded situation. That is a piece of insulator. It could be wood. It could be air. It could be plastic. It could be anything that is an insulator. It could be rubber. It could be anything like that. But now we're going to be looking at a copper wire. So in looking at the copper wire, we're going to change the subatomic particles, and I'm going to show you what happens in that scenario. Here we go. So we go back to the copper wire. We have a subatomic particle, the nucleus of the atom, it's right here. We have an electron that is here and here in stable orbit, right there. But then we have a free valence electron, negatively charged, that is not in a stable orbit because there is no electron over here. It doesn't exist. Okay? The electron is non-existent. This would be indicative or a conductor material. It could be brass, it could be copper, it could be gold, it could be aluminum, it could be anything that is a conductor. What makes it a conductor is the fact that it has a free valence or free electron. So with that in mind, what happens is if I take a magnet, and I'm going to show you what I'm going to do here. I have a magnet, it's a bar horseshoe type of magnet like this. I have north and I have south. And this has what's called magnetic lines that go this way. I'm just avoiding the contaminating my chalk right here, my marker right here. These magnetic flux lines, when they come into contact with a conductor, it will take this electron and knock it out of orbit. That's what magnetic fields do. When they come in contact with the conductor, it knocks that electron out of orbit. And it hits another electron, and it might knock two electrons out of orbit. And then that'll hit another electron, and it might knock out 4 electrons or 8 electrons out of orbit. And what it does is it produces what's called voltage. Okay? That's what happens. That's how electricity is made. It's simple. It's just putting a magnetic field around a piece of copper or conductor and creating a voltage. Now, that voltage is the same thing as electrical pressure. Electrical pressure would be like air pressure in a pipe. Let's look at this as a compressed air pressure, like an air hose. There's nothing going out of that pipe. It's closed. It's sealed off. Okay, so electrical pressure, air pressure, we're going to look at for now is the same thing, but it's sealed off. So now we have, say, 120 volts, or we could say we have 120 pounds per square inch as an example, analogy, okay? That's what we're doing. As soon as I open up this end and let some of that air out, or voltage out, then what happens is the voltage drop. And amps, which is current flow, goes up or increases. Okay? Because amperage or current flow is going out. If I let air out of this pipe, then we go from 120 down to 30 or 20 or whatever, depending on how much of that pressure we're losing out of that hole right there. The same exact thing is true for electrical. Now, I need you guys to understand the theory of this because we're going to be building on that when we come into relays and conductors, and we come into inductors, we come into solenoid circuits and things like that. Ignition coils, all of that's going to be based on that example right there. So, that's our electrical theory. All right, so that's A. Mark that down as A. Part A. I'm going to write it down here so you can see it. Part A. There we go. Part A has, number 1, voltage is equal to electrical pressure. Okay? Amps is electrical flow or current. Okay? Now there's one more thing I want to bring into your understanding in electrical theory. We have one more part to this puzzle here, and this is called resistance. And resistance is the same thing as ohms. O-H-M-S. It's a little horseshoe there, and it's called an ohm. That is the resistance in that circuit. So what would be the resistance here? Well, let me show you. Let's say I put a kink in the pipe. I take this pipe and I put a great big massive kink in it right there. Well, you can see now that I've reduced the amount of flow that can go out that hole. Even if I open that hole all the way up to its full opening, I still have that resistance right there in that kink in that pipe. So I want you to think of electrical resistance as a kink in the pipe. That kink in that pipe is extremely important to understand because a man named Ohm had created this thing called Ohm's Law. Now, Ohm's Law is going to be dealing with these 3 things here. So I'd like to welcome you now to part 2. Picture of that. Make sure you can see what that's all about. And now, or part A, excuse me. We're going to go to part B. Here's part B coming up next. Here we go. Part B. We're going into part B, and this is going to be a little bit more intense. This part B has made me more money in my life than anything else, and I will show you how that works in real life here in a minute. But first we have to understand what part B is all about. So here we go. So I'm going to say this. I'm going to say that volts is equal to amps times resistance. And I always put that little horseshoe there so you can see what it means. That's the equation. It's also written like this. E. E stands for electromagnetic flow, which is the volts. Don't worry about it. E is equal to amps, which is I, times R, resistance. Okay? And I always put that little ohm signature there so you can see what that is. That equation and this equation are the same. They're exactly the same. That's just volts times amps. Volts is equal to amps times resistance, and that gives you a known quotient. Okay, so let's go in to part B. This is the number 1 section of part B. Number 2. So how do I use this equation so I don't have to use a lot of math to figure out what's going on? So here we go. I make a pie, a big old circle. I cut it in half, and then I cut it in quarters. Here we go. I put volts up here, and I'm going to put E up here so you can remember it. I'm going to put amps right here, or I'm going to put I, so you'll know what that is. And then R, or the little horseshoe, is resistance, and I'm going to have to abbreviate it as resistance. I'll probably A-N-C-E. There we go, resistance. Okay, so that's going to be the same thing as writing it this way. E/I/R with a little horseshoe. Okay, so what if I have, let's say, 100 volts, and I have 2 ohms of resistance. What are my amps? Okay, so this is resistance. This is volts. What are my amps? Okay, well, take a look. I don't know what my amps are. The question is here. This is my question. Where are my amps? I cover it up. Now that it's covered up, and I'm going to erase it so I don't know what that is. I'm going to erase it. Now all I know is I can take 100 divided by 2, and that means I've got 50 amps. See, I covered it up. There is resistance divided into voltage, done right here, gives me 50 amps. This is my I right there. Now, let's say that is part 2. Let's go to, that's part 2, and then bullet this one for me. Put a bullet right there. Then we got another bullet right here, okay? Here's the next bullet. I got to erase this to get room to write. Let's say I have 100 volt, no, I have 50 amps. I have 2 ohms of resistance. What is my volts? There's the big question. What are my volts? Simply cover up the volts. That means amps times resistance. 2 times 50 is 100. Now I know that 100 volts. This is called Ohm's law. You have to know this to fix cars. You cannot fix cars unless you know that mathematical equation. I need you to study that pie chart. I'll write it up again so you can see it a little easier. Here it is again. I'm going to write the same thing as I did here. I'm going to do it again, only a bigger pie chart. I'm going to put volts, which is E. I'm going to put amps, which is I. I'm going to put resistance, which is R. And all you need to know is the unknown. You just cover it up, and it'll give you the equation that you need. This will be part of your exam when you come back next week. So far, welcome to part B. That is part B, 1, 2, and if you want to put a third one down there, use that as notes. things that you want to write down extra. So this would be part 3 equals notes. Okay, now we're going to get into some more cool stuff. Now I'm going to show you how to make money on this little equation. So get ready. This is going to be an example, and this will be a really good example. Here we go. I have a fuel injector that's bad. Now normally, my one fuel injector has 12 volts that goes to each injector. And on these 12 volts, I'm just going to say that the resistance 2 ohms, just so I'll make it easy. But I don't know what the amperage is. I do know I measured the ohms with my meter, and the meter that I use is those electrical meters we have. We measured this is known. We measured the voltage, that is known. We don't know what the amps are. Okay, this is part C. Okay, so what are my amps? So I draw my pie chart. I go my volts, or E, same thing, okay? Amp, we don't know what the amps are. And the resistance, or little horseshoe, is 2 ohms, okay? 2 ohms. So what do? 2 into 12 is 6. So there you have it, 6 amps. Wow, this is going to be 6 amps. No more question about this. This is a good fuel injector. Those numbers all match up. But now, let's say I got a fuel injector now that is my bad injector. So I'm going to go ahead and write my bad injector down. Fuel injector goes like this. I measured, I got 2 ohms right there. Okay, I know I got 2 ohms. And I know I've got 12 volts, right? But wait a minute. I got a bad injector. What I really have is 1 ohm. Not my 2, but 1. Well, that's telling me 1 into 12, right? How am I going to do that? How do I figure amps? Well, I got 12. I got 1 ohm. This is going to be 12, isn't it? So 12 amps. 12 amps is way too high. It should be this one here. But here, that's the wrong number, and that's the wrong number, and that equals a bad fuel injector. And that's how you check fuel injectors in a car without having to drive them, hook up meters, or hook up special equipment. Just a voltmeter will help you do that. I hope you understand that in part C is a functional way of using, starting with bullet number or subheading number 1, is comparing the good with the bad equals a diagnostic outcome. You can make money just knowing that much right there. Not very many people know about that. Okay, that is part C. Welcome now to part D. Here we go. I'm going to write it up here. And we'll write it in green so you can see it's a little different. Part D. Here we go. Okay, now that you know Ohm's law, you've taken a few notes, you understand it. Remember what I told you about the magnet? We have a wire like this. We have a magnet with a north and a south pole, horseshoe magnet. It's got these magnetic lines of flux, or these magnetic lines, they call flux lines, that kick out the atoms down the wire. Okay? This is our horseshoe magnet, south pole, north pole. Magnetic lines of flux kicking the electrons down and making voltage. This whole process we call electromagnetic induction. Okay, that's how it works. Now I want to give you an example, help you have a mental map to understand this process right here. Because all we're doing is talking textbook right now. Let's jump out of the textbook and let's go into a practical demonstration. Here it is. Part D, electromagnetic induction. Number one is this, okay? That is an induced voltage induced by a magnet, or a magnetic lines of force inducing voltage, okay? Here goes the example. I'm going to show you a real life situation here. Part two. Now you can draw this any way you want. I don't care how you draw it. My artwork really is bad, so I apologize. But one day I was irrigating. I was watering a field. We had a sprinkler system. And we had power lines. Now I'm just going to draw a pathetic power line here. And we had the insulators here and the insulators here, okay? And the power lines ran down this way. Here's a power line. Here's a power line here, okay? Here's the pole. Here's the power pole. Not a telephone pole, it's a power pole. I was a journeyman lineman for 17 years, and they're not telephone poles, they are power poles. Okay, so we have a power pole there. One day, I was walking, carrying pipe. It's aluminum. And my feet, you can show my feet here. My feet were in water up to my ankles, and I had some aluminum pipe in my arms, carrying it across the field, walking across the field in water. All right? So here I am. This is me. Sunglasses. Oh, see, I had some sideburns. There we go. This is me. Had a turtleneck sweater, maybe some sunglasses. Right? All right, that's me. And I'm carrying this large pipe. Okay, and I'm down here. I got my feet down here in the water, and I'm carrying the pipe with my pathetic drawing. I'm holding onto the pipe right here, like this. And the water is up to my ankles. All right? Well, guess what, folks? These power lines produce a magnetic lines of field. They go out perpendicular to the wire, like this. Okay, let me get another purple marker so I can show you what I'm talking about. So this magnetic lines of force going out like this, perpendicular. This is perpendicular to the wire. This is perpendicular. This is perpendicular, what I'm drawing right here, okay? These great big lines of force got down into this pipe. Here's my pipe. Well, what did my pipe do? My pipe cut through those lines of force. As I moved the pipe through here, it cut through those lines of force and induced a voltage into the pipe. And because I was grounded with shoes in soaking wet, dirty water, this pipe picked up a voltage and it knocked me down, literally knocked me down, because I had 4,160 volts up here producing magnetic lines of force clear down to the ground. And as the pipe moved through these lines of force, it produced a voltage. So the end of this subject goes like this. You must have movement, either magnetic movement or conductor movement, going through these magnetic lines of force to produce a voltage or a voltage pressure. There has to be movement. If I was standing still, I wouldn't feel a thing. But as I moved across the field walking, I was cutting through these lines of force that you see here in this drawing, and that is why I got knocked down on my rear end, because I cut through those lines of force. So, induction, either electro or magnetic induction, requires movement. You have to either move the conductor or move the magnet to to produce the voltage. This is the very fundamental basis and understanding of electrical. I can't stress this enough. This is, number one, magnetic induction. Number two, if it's this is electromagnetic, or if I have that north and south pole magnet that I showed you guys, north and south, my conductor is here, and I move the magnet in and out, this way and this way, moving in the magnet back and forth, producing these lines of force. The magnet moves or the conductor moves, either way will produce a voltage. I need you to understand that. That's part 2. All right? So now that we've got understand part D, and we've subheaded it part 2, let's jump into the automotive portion of this whole thing. But before we do that, I want to review, because always I go too fast, I cover too much ground, and students end up trying to figure out what I said at the end of class. So I'm going to go through it just one more time. This is where you're going to go back in your subheadings, and we're going to figure this out. Okay, so let me clean off that board a little bit better. Okay, hold on. I'm going to clean this board up a little bit better than it looks right now. Sorry for the delay. Just bear with me here. Don't lose your concentration. Here comes our review. Okay. In review, we have a few concepts we need to be looking at. And here they are. All right. E is voltage. Voltage is electrical pressure. Electrical pressure is potential energy. That's potential. Potential energy. Okay. Next we have I is equal to amps is equal to current flow is equal to work done. Can't get any work done without current flow. Work done, current flow, all of that, it is not the voltage that kills you, it is the amps that kill you. This kills, this is no kill. It takes current flow to kill you. It doesn't take voltage. That's why a bird can land on a 4160 or 12,000 volt primary line. Doesn't hurt the bird at all because there is no current flow. Kill, no kill. Just to help you remember it. Resistance is equal to ohms, which is the horseshoe, which is resistance, which is the kink in pipe. As an example. That's just an example. All right? There is our analogy. Okay? Takes current to kill you, but voltage cannot kill you. Keep that in mind. Okay? Now, with that in mind, we also have Ohm's law. Ohm's law is our pie chart. We have volts, which is E. We have amps, which is I. And we have resistance, which is our little horseshoe, and it is R. If you don't know which one it is, just cover it up. What's my amps? I cover it up. It's resistance divided into voltage. What's my voltage? Amps times resistance. What's my amps? Or my resistance? It's amps divided into voltage. Simple, easy, real easy, money-making information. You have to know these fundamentals or you can't fix anything in a car. Now, we're going to get down to some practical things in part E, I think it is. Here we go. Practical understanding. Now, this is going to be some really interesting stuff. So, you're going to go to work in a shop. And a guy in the shop says, "Hey, buddy, I want you to come on over here. Now, I want you to remember, we've taught you this before. We have a plus, we have a minus battery. This is a lead acid car battery, okay? We have a post here and a post here. All right. The guy in the shop says, "Hey, young man or young lady, I want you to wet your fingers down and I want you to touch these two poles right there." Is that going to shock you? Nope. Not at 12 volts. Not really. Okay? Well, let's go through what's going on here. Okay? So let's take a look and see what's happening first before I go into this why it won't shock you. It takes 12 volts because, look, I got a wire here, got a light here. This is a light. This represents a light. Okay? Now I go down here and I got a switch that goes to there. That light is off when the switch is open. Light is off. When the switch is closed, the light is on. What made that light turn on was current flow. Current went from the positive to the negative through the light and caused the light to turn on. That's what happened. All right? It was a good conductor and it went through and turned the light on. Why didn't you get shocked when you touched the two terminals? What happened? Here's what happened. Generally speaking, and not in every case, this is just a general rule of thumb. If you're dry shoes, dry clothes, wet fingers won't matter. Your shoes are dry. Usually takes about 50 volts to penetrate your skin and cause you to feel an electrical charge because it takes 50 volts to get the amps up enough to feel them. So the amps have got to be usually around 1 amp before you're going to feel anything. 50 volts is the pressure. How much air pressure determines penetration. 50 volts are going to penetrate your skin, not 12 usually, not always. But depending on how well you're grounded. Now, if I hooked you to a copper wire that was driven into the ground, yeah, you might feel something. So understand there's a certain amount of resistance that makes that possible that you don't get shocked. That's a practical application of what we're learning today. That is called a series circuit. Write it down. So part E, number 1, is a series circuit. It's got an out and an in. Period. End of the story. Now, watch this. Number 2. Number 2, we are going to make what's called a parallel circuit. This is a parallel circuit right here. When I hook things in parallel, that's what it looks like. That is a parallel circuit. Okay? So, here's the bottom line of what parallel and series does. Let's make sure you're taking notes. If you're not taking notes on this, you're missing the point. So, number 3, and here we go with number 3. This is part E, number 3. Here we go. I have 2 car batteries. Car battery A, we're going to call this car battery A. Then I got car battery B. Here we go. Okay, I got let's see, this is negative. I'm going to call this one negative. And this is positive. All right. 12 volts. Okay. And this is a car battery. There we go. If I take and connect these two batteries in parallel, this is what it would look like. As negative to negative, right there. Let me write it so you'll see it better. I'm going to do it a little bit different. Hold on. Negative to negative. Positive to positive. I'm going to hook it like this. Bear with me. Getting all my caps mixed up here. Positive to positive is going to look kind of like this. These two batteries are hooked up in parallel. So this goes here, plus. This goes here, minus. And I can take a light bulb or a meter. Let's say a meter. I'm going to take a voltmeter, not a light bulb, excuse me. But I take a voltmeter here, put it on the positive, connect it on that one, and I read 12 volts. What do I have? I've connected them in parallel, and that equals same voltage as the one battery. Battery A and battery B, both 12 volts, but when I hook them up in parallel, which I've done here, negative to negative, positive to positive, I read 12 volts. All I did is make the battery bigger. That's all I did. Like an air compressor. I made the storage tank bigger. That's all I did. It's got more storage capacity at the same voltage. So in item number 3, parallel is equal to more storage or cold cranking amps and same battery voltage, which is 12 volts. We're just saying 12 volts for now. It's 12.6, but let's just say 12 for now. That's the parallel phenomenon. Now, let's take another look at what we're going to do. We're going to do something a little different now. I'm going to take this out all together. And now I'm going to call this positive. I'm going to call this negative. Negative to positive. Negative. Positive. Okay? So negative to positive, negative to positive. Now I go to read this, and what do I got? Well, here's what I got. 24 volts. Yeah. What I did is I increased the voltage, so in series, this is what I did. Number 3, which is number 4 actually, excuse me. Number 4, series. I have less storage and, or excuse me, same storage as one battery, so same as the one only, but I have more battery voltage. What am I saying? In this scenario, series is equal to more voltage and parallel is equal to more storage capacity, or CCA. Boom. More voltage, same storage as one battery. Please understand that. That is extremely, extremely important for your understanding when it comes to electrical. You understand this much, you're well ahead of some of those other guys out there working in the field today. Not many people really can figure this out very well. Okay, we're coming to the end of it now. We're coming close to the end of this. Part F is where we're going to end. So I need you guys to pay attention to part F because it's really important. Part F is going to tie everything together now. Learned a few things. When it comes to part F, we learned that, number one, there are really a whole bunch of different circuits. There's a series that's got a battery, and this is a symbol for a battery. This is negative, this is positive. Here's our light. Going back through a switch, and our light turns on. This is on. That's a series circuit. Number two, parallel. Looks like this. Okay? Parallel circuit looks like that. Number three, a series parallel circuit is going to look something like this. This light is in series with these two parallels. Series, parallel, circuit. What are the circuits? There's number one, series. Number two, parallel. Number three, series parallel circuit. Those are the three types of circuits. That's part F. Number four, there's three conditions of a circuit. Three of an electrical circuit. Here we go. There is an open. This means if I open up the circuit here, this is open. The open is right there. I broke the circuit. That's an open circuit. See that? Open. So part one is open circuit. Okay? Then there is a short circuit. A short circuit would be something like this wire here going to ground. Here's the symbol for ground. It's shorting out. Instead of going back to the battery, it's going down here to ground. There's a second point of contact called a short circuit. That's a short circuit, okay? All right? And then there is a resistance in the circuit. In other words, it doesn't go straight to ground, really. Only some of it goes to ground. Maybe there's another light bulb you don't know about that's going to ground, and it's not completely shorted out, but it's kind of shorted out. The kink in the pipe isn't that bad. That is a resistive circuit. Three conditions of the circuit. Open, resistance. There's open, short circuit, there's a resistive circuit, and then actually there's four, and it's a closed circuit, which is when the switch is closed. When the switch is closed, the light is on. When the open circuit's open, the light is off. When the short circuit is shorted, you have off. And when you have a resistive circuit, you have on and a little bit of off. Sorry. actually 3 conditions. My bad. I think of this sometimes. This is not normally taught in school. They only teach these 3 things here, but I want you to get familiar with the resistive side of the circuit. Okay, that ends our lesson for today, but I want to go through a quick review just to make sure we're covering all of this stuff. And in covering all this stuff, I want you to go through some concepts just really quick. Don't lose your concentration. Stay with me. Here we go. A symbol. Symbols for batteries look like this. This is a battery. Okay? This is a ground. Kind of looks like this. Let's get the color here maybe. Ground's going to look like this. The wire on it. Okay? Switch. It's going to look like this. That's a switch. A connection. It's just going to be a wire. Here's a connection with another wire hooked to it. Maybe there's 2 connections. That's a connection. Those are the 4 symbols I'm going to require you to remember. Don't forget Ohm's law. Voltage over amps times resistance, or EIR. And don't forget the little horseshoe. That will conclude our lesson for today. Very, very, very important that you understand these basic fundamentals so we can build on these to make the practical application work. We're going to film what we did today, starting with our filming today. Look at what we've done. We filmed our soldering unit today. Take a look at this all along here. We've got all our tools set over there. And we have our solder boards over here where our students are building their solder boards. I'm going to turn them around so you can kind of see them. Putting their names on them and building their solder boards. Get ready for the test next week. I think it's around the 12th. Whenever that is, I'll see you on Monday and Tuesday, students, so be prepared. Thank you for joining us today.